Welcome to our quantum deep dive. Today, we are exploring one of the most mysterious and honestly most powerful particles in the entire universe, the antiproton.
That's right. This whole explainer is based on a really in-depth essay by Jörg Schneepatt, and we're going to unpack why this one tiny particle holds the key to some of the biggest questions you can imagine, including why we even exist at all.
Okay, so let's just jump right into it with what has to be the universe's greatest unsolved case, the mystery of the missing antimatter. And look, this is not just some small cosmic accounting error. The answer to this question underpins the very fact that everything you see, well, that it exists. Right. According to our best understanding of the Big Bang, that first fiery moment of creation, it should have cooked up matter and its perfect mirror image, antimatter, in precisely equal amounts. And if that had happened, if the universe had played by its own rules, they would have instantly found each other and, poof, annihilated in this final, universe-ending flash of pure energy. The cosmos would just be a vast, empty sea of light, and that's it. But, obviously, that's not what happened. We're here. The Earth, the stars, entire galaxies are here, and they're all made of matter. So the big, universe-defining question is, what happened to all the antimatter? Why was there this tiny little imbalance that let matter win? So, to solve this puzzle, physicists are basically acting like cosmic detectives. They are hunting for a flaw in that perfect symmetry, some tiny little crack in the mirror between matter and antimatter that could explain everything. And their best tool for the job, the single piece of evidence they are putting under the most powerful microscopes in the world, is the antiproton. You could say it's their prime suspect. So what is an antiproton exactly? Well, the simplest way to think about it is as the proton's perfect but opposite twin. A proton, as you probably know, is that key particle in the nucleus of every single atom that makes up our world, and it has a positive charge. Well, the antiproton is its perfect mirror image. It is identical in every way you can measure it, like its mass, its spin, but it carries a negative charge. It's really the heart of antimatter, just like the proton is the heart of matter. And what's just truly incredible is how identical they are. I mean, just look at this breakdown. The mass is the same down to the smallest decimal place we can possibly measure. The spin, which is this intrinsic quantum property, kind of like a tiny spinning top, is also identical. The only differences are that electric charge, which is perfectly opposite, and their inner building blocks. You see, a proton is made of these fundamental particles called quarks, 2 up quarks and 1 down quark. So the antiproton? It's a perfect reflection, made of 2 anti-up antiquarks and 1 anti-down antiquark. And this perfect mirror property, well, it leads to the most dramatic and violent outcome in all of physics. If an antiproton ever meets a proton, they don't just collide like billiard balls, they annihilate.
They completely vanish, converting 100% of their combined mass into a burst of pure energy. It perfectly follows Einstein's famous equation, E equals mc squared. And just to put that in perspective for you, a nuclear bomb is less than 1% efficient. This is 100% efficient. It is by far the most powerful energy release known to science.
This particle's story didn't even start in a lab. It started on paper, in the mind of a genius. Back in 1933, the physicist Paul Dirac was working on his beautiful equations describing the electron, and he noticed something odd. The math allowed for a second solution, one that described a particle with the exact same mass but an opposite charge. He was in effect predicting antimatter from pure theory. And it was a prediction so wild it took over 2 decades for our technology to catch up. Finally, in 1955, 2 physicists, Chamberlain and Segre, used a powerful new accelerator to actually produce and detect an antiproton, a discovery that rightly earned them the Nobel Prize. And today, that legacy continues at places like CERN, which has an entire facility dedicated to just creating, taming, and studying these elusive particles. So how in the world do you get your hands on something that vanishes the second it touches anything made of matter? Well, it's an absolutely incredible feat of engineering. First, you take regular protons and you accelerate them to almost the speed of light. Then you just smash them into a block of metal. The sheer energy of that impact, again, think E equals mc squared, it creates this spray of brand new particles. And if you're lucky, a few of them will be antiprotons. But they're moving way too fast to study. So the antiproton decelerator does exactly what its name says. It uses these powerful magnetic fields to catch them and slow them way, way down, step by step, until they're moving slowly enough to be captured in what's basically a magnetic bottle, a device that holds them suspended in a near-perfect vacuum, totally isolated from our world of matter. So, why go to all this unbelievable trouble? Well, scientists are testing one of the most fundamental ideas in all of physics, a principle called CPT symmetry.
Now, this principle says that the laws of physics should be perfectly symmetrical. So if you were to take any particle interaction, swap the particle for its antiparticle, then view the whole thing in a mirror, and then run the film backward in time, the outcome should be exactly, perfectly the same. It's really the ultimate test of nature's fairness.
Because if it's not perfectly fair, even by a tiny, almost undetectable amount, well, that tiny crack in the mirror could be the very reason our matter-filled universe exists. And this is the whole point. This is the entire motivation for these massive, unbelievably complex experiments. They are designed to measure the properties of a proton and an antiproton to a degree of precision that is, it's almost impossible to even wrap your head around.
They are looking for any discrepancy, no matter how small. Is the mass exactly the same? Is its magnetic character a perfect mirror image? Or is there a tiny flaw?
And the results so far are, well, they're absolutely staggering. The base experiment at CERN managed to trap a single antiproton and measure a key property called its magnetic moment. And then they compared it to the proton. So what did they find? They are identical to a precision of more than 11 decimal places. Any difference that might exist is less than 1.5 parts per billion. To really grasp that, imagine measuring the distance from Los Angeles to New York. This is like being accurate to within the width of a single human hair. It's just unbelievable. So the astonishing conclusion here is we haven't found the crack yet. The reflection in the mirror is, for all intents and purposes, perfect.
And this result is both a stunning triumph of experimental physics, and paradoxically, it actually deepens the cosmic mystery. It tells us the simple explanation probably isn't the right one. The reason for the matter-antimatter imbalance must lie somewhere else, maybe in the behavior of other particles, or in physics so extreme it only existed in the first microsecond of the Big Bang, physics we haven't even discovered yet.
But while that fundamental mystery remains unsolved, the incredible technology that was invented just to trap and study antiprotons, well, it's now opening the door to some amazing, almost science fiction-like applications right here on Earth.
Yeah, it turns out the very same properties that make antiprotons so volatile and so difficult to handle also make them incredibly powerful tools. The potential is enormous, spanning revolutionary ideas in medicine, deep space travel, and even the future of computing itself. In medicine, for example, we already use proton therapy to target cancers. Protons have this clever little trick where they release most of their destructive energy right at the end of their path, smack dab inside a tumor. It's called the Bragg peak. Well, antiprotons do the exact same thing, but then they have a second act. They annihilate with protons right there in the cancer cells, releasing a powerful secondary burst of energy. So it's like a 1-2 punch. That extra kick from annihilation could make them way more effective at destroying even the most stubborn tumors, with potentially even less damage to healthy tissue. And what about space travel? That 100% mass-to-energy conversion we were talking about makes antimatter, at least in theory, the most potent rocket fuel imaginable. Just a tiny amount could power missions to other stars, something that's completely unthinkable with current technology.
The energy density is about 1 billion times higher than the chemical reactions we use in today's rockets. Now, of course, the challenges of producing and storing enough antimatter are immense, to say the least, but the possibility of interstellar travel is just too great to ignore.
And its potential even stretches into an even more futuristic field, quantum computing. Right now, the greatest enemy of a quantum computer is interference from the outside world, what physicists call environmental noise, which just corrupts the fragile quantum states of its qubits. But think about it, an antiproton, held in the perfect isolation of a magnetic trap, is almost completely shielded from all that noise. This could allow for incredibly stable and long-lived qubits, which are the fundamental building blocks of quantum machines that would be far more powerful and reliable than anything we can build today.
So, we're left with this final thought. We started this whole journey with the antiproton as a clue in this grand cosmic mystery. Why are we here? And for now, it remains a tantalizing, unsolved clue. But in the process of chasing that fundamental answer, we are forging the tools for a technological revolution.
We're developing technologies that could redefine medicine, transform space exploration, and build the next generation of computers. The quest to understand our origins is, in fact, simultaneously building our future.
We'd like to thank you for joining us on this deep dive. This explainer was inspired by the really detailed and fascinating essay from Jörg Schneepat. For more information and to read more of his work, you can visit schneepat.de. Goodbye!
Schneepat.de is a private project by Jörg Schneepat dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.